All right, we're going to spend some time going over examples using these sum and difference identities. Um, if you have the identities already, you probably have these written down. If not, take a second to put these 6 identities down. They're going to help us to prove other identities, evaluate some values using either the sum or difference of different angle values. So our first example is going to be an evaluating example. We want to find the cosine of 15 degrees. So the first thing that I want you to be able to identify is how you would get 15 degrees using angles that you know something about. Well, we have a couple of different ways of going about that. We could take 60 minus 45. We could take 45 minus 30. I'm just going to use 60 minus 45 in this example, although 45 minus 30 would end up giving us the same value at the end. So once you figure out what two angles you're going to use, you have declared kind of what you're calling this u and this v in the formula. So we're looking at a difference formula. So I should probably point out these here. We've said that u is 60 and v is 45. We're doing cosine, so this is the formula that we want to use. Product of the two cosine values added to the product of the two sine values. So we're going to take the cosine of 60 times the cosine of 45, and we're going to, add. Cosine is always the opposite, so if it's a difference, we're doing addition right here. And then we're going to do the sine of 60 and the sine of 45. And then hopefully these we just have memorized at this point in time. If the two angles you're using are two acute angles, 30, 45, or 60, then this is pretty straightforward. You put the values in. Got to remember how to multiply fractions together. Numerator times numerator, denominator times denominator. You can multiply radicals together as long as they're the same type of radical. They're both square roots, so we can multiply them together. Oop, there should be a 4 here. And then we will combine this into one expression at the end because they have a common denominator. So that would be the cosine of 15 degrees as an exact value. The thing I'm going to point out here, because I don't think we have this pop up on our examples, but it would pop up in your homework, is it might not always be an angle that you can grab right from your trig table. For example, if you were going to find the cosine of, I don't know, how about 105, okay? We could use, actually we could use 60 and 45 here, but that's what happens when you just make a example up on the spot. I'm going to do this a little bit different way. I'm going to use 135 minus 30. And even though 135 isn't an acute angle, we know the cosine and sine of 135. So we can use that to help us identify these values. Sine 30 right here. This guy and this guy, we know what those are. We know that those have a reference angle of 45 degrees in the second quadrant. So we know cosine is going to be negative, sine is going to be positive. So this would end up being negative here, and the cosine of 30 is just square root of 3 over 2. Come back to the sine in a second. Sine of 30 is 1/2. And then we would just use 45 degrees as a reference angle. So the cosine and sine are both square root of 2 over 2. I've just made sure that cosine is negative because it's in the second quadrant. So after we'd go through here and multiply these together, we'd have square root of 2 there, we'd have negative square root of 6 there, so I put the square root of 2 in front because it's positive, minus the square root of 6, and it would all be over 4 after we add the two fractions together. So there's a quick example of using an angle that is not an acute angle. We still, as long as it's got a reference angle that we recognize, we can still evaluate it. So I'm going to get rid of these because this isn't actually on this sheet, but that might help out with some homework problems. All right, so now, the other thing we're going to use these angles, or these identities to do is to identify or verify other angles, other identities. So for example, if I want to verify that the cosine of pi over 2 minus x equals the sine of x, then I can use the cosine difference formula and expand this out. Cosine difference has addition in it. Now I've expanded that out. Now I just want to evaluate the angles that I know the values of. Cosine of pi over 2, think about where pi over 2 is, right there. We've got 0, 1, so the cosine is 0 times the cosine of x. Sine of pi over 2 is 1 times the sine of x. So this becomes, obviously, 0 times cosine of x is 0, plus 1 times the sine of x. We can just go right to the sine of x there. So we verified it. We started with the left-hand side. We ended with the right-hand side. All right, let's try another one of those. Now we have sine of pi over 2 minus x. So I'm going to need a sine difference formula, which is sine cosine minus cosine sine. Same values as before. Sine is 1. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. That's multiplication. So now we have cosine of x. Verified that identity as well. Okay, these, which look more complicated, are actually some of the easier ones that we do. We just need to recognize what sort of identity is being used there. It goes sine cosine plus cosine sine. So this is the sine sum formula. U is 22 degrees, and V is 13 degrees. So this is simply an expression that would evaluate the sine of 35 degrees. And then we just express it as the sine or cosine of an angle. We're done. We don't have to evaluate it because we can't find an exact value of that. We would just leave it out how it is. And the next one here, we have sine minus cosine cosine. So this kind of looks like the cosine sum formula. But in order to use that, we'd actually have to pull a negative out of this. So we've got to leave it out in front. You're not multiplying the whole thing by -1. You're pulling a negative out. So that would make the cosine of x times the cosine of 2 of x positive now. And then that product of sine x sine 2 of x is negative. So I'm going to put it second. So I'm going to bring that negative down. And then this stuff is a cosine sum formula. So it is, the cosine of the sum of what two angles? There's U, there's V, x and 2x. So this is negative cosine of 3x. And we have a cosine formula because it goes cosine, cosine, and then sine, sine. Because it's got a difference or subtraction right there, we know that it's going to be plus. Cosine is always the opposite. And then we just need to put in our U and our V. And then we just got to find a common denominator here. I'm just going to kind of do this. I guess we'll just continue the problem. I was going to do it in the margin, but common denominator would be 12. So this would be 4 pi over 12 plus 3 pi over 12. After getting the common denominators, we add those together. This is actually the cosine of 7 pi over 12. So, the reason why we do problems like this, especially this one, is, in your homework on the quiz, you might ask to evaluate this. You might be asked to evaluate this. So then you need to realize, okay, I can turn this into that, and then expand it out like that, and then evaluate from there. So it's good to see kind of the build of certain angles like 7 pi over 12. Our next type of problems here, we're going to be proving some reduction formulas. So these are not identities that we've worked with before, but they are identities that we can prove using the identities that we have. So we're going to start with the left-hand side here. Sine of x plus pi. Expand that out. Remember, my final answer should be negative sine of x. I'm going to expand that out. Sine of x cosine pi plus cosine of x sine of pi. Pi right there. Negative 1, 0. Cosine is negative 1. So we've got sine of x times negative 1 plus cosine of x times the sine, which is 0. So that product is going to become 0. We're just left with negative sine of x. So we've proved that identity. Going to start with our left-hand side here. Now let's work to get to the right-hand side. You have to start with the left-hand side on these. There's really nothing you can do with that sine of x to work to the left-hand side. So let's start with the left-hand side and work to the right-hand side here. We're going to expand. We've got a cosine sum formula, which goes cosine, cosine, minus sine, sine, 3 pi over 2, 0, negative 1. So cosine is 0. And the sine of 3 pi over 2 is negative 1. So we have negative sine of x times negative 1, which is simply sine of x. All right, now we're going to prove a tangent reduction formula. I'm going to start with that left-hand side again. So I'm going to kind of treat this how I think most of us would. To start with, we have a tangent difference formula. I'm just going to write what the tangent difference is right here, so we have something to reference. You can just obviously look back at the front side of the sheet, but the tangent of u minus v is equal to the tangent of u minus the tangent of v all over 1 plus the tangent of u times the tangent of v. So we start filling this out. Tangent of theta minus the tangent of 3 pi over 2 over 1 plus the tangent of theta times the tangent of 3 pi over 2. Now we need to evaluate what we can, which is the tangent of 3 pi over 2, but there's an issue. Tangent of 3 pi over 2, I'm just going to write tangent, is undefined at 3 pi over 2. So we can't do it this way. So we've got to think of something else. All right, so let's start from scratch. So I'm not going to cross that out. I want to leave that there, but I'm going to start the problem over again. So there's got to be some other way. Well, remember, we do have a definition of tangent that it's sine over cosine. So sine of theta minus 3 pi over 2 over cosine of theta minus 3 pi over 2. And then each of these, make this a little bit more legible, we can now expand using our difference formulas. Remember, cosine difference has addition. And all of these are defined. We can find all these values. All right, so the cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is negative 1. cosine of 3 pi over 2 is 0. And the sine of 3 pi over 2 is -1. Notice remember when you evaluate a trig function, you don't need to write sine and cosine anymore. You just put the value down. So we know in the top here that this is going to equal 0. In the denominator, this is going to equal 0. And in the numerator, we're just left with negative cosine of theta times -1. Well, that's just going to be cosine of theta. In the denominator, we have negative sine of theta times -1. That's just going to be sine of theta. Probably a good time to look back at our right-hand side, make sure we're heading in the right direction here. Ooh, let's see here. So you see the negative. My guy must have done something wrong. So I'm looking back. That was correct. That one is not, though. Make sure you fix that and then bring that plus over properly. So this should actually be negative sine of theta. So we are perfect. Got that right-hand side. Nice thing about verifying problems is you can catch your own mistakes. Or maybe I should just look at my notes as I'm working here. All right, last one. A little bit more complicated. So we've got sine of 3u. You can't call this sine of u plus u plus u. Okay, so I'm going to start with my left-hand side. You can't do this, so I wouldn't even write this, but you can't do this. There is no like triple sum formula. That's just not possible. What we can do, though, is call this the sine of 2u plus u. And now expand that out using our sine sum formula. So sine times cosine, sine of u, cosine of v, and u is 2u, v is u, plus cosine 2u, sine of u. And now each of these we can now expand. That sine of 2u is going to become sine of u plus u. And if you already done section 5.4, depending on when you watch this video, we actually have something that we can replace this with called a double angle formula. We haven't got there yet in 5.3, so I just need to expand that out again. And now I have the cosine of u plus, and then this guy here, cosine of 2u, I can call the cosine of u plus u, and then that is being multiplied by the sine of u. So now we have to expand each of those out. The sine of u plus u is going to become the sine of u, cosine of u, plus cosine of u, sine of u, which are really the same two products. Doesn't matter what order you write that in. And then that is being multiplied by the cosine of u. And that's being added to, now we're going to expand that cosine of u plus u. That would be the cosine of u, minus sine of u, and that's being multiplied by the sine of u. All right, it's a little daunting at first, but we're almost there. So in purple here, we really have the same two things here being added together, and that cosine is being distributed as well. So I'm going to just take kind of 2 steps to get there and just say this is 2 sine of u, cosine of u. That is being multiplied by that cosine of u, plus, and then here we have, I'm going to call this cosine squared minus sine squared. Make sure you keep that in parentheses. That is being multiplied by sine of u. I didn't keep this guy in parentheses right here because there's no addition or subtraction. It's really not necessary. In fact, let me write my u a little bit nicer. In fact, I can now multiply these two cosines together and call this 2 sine of cosine, sine of u, times cosine squared of u. And that's being added to, and I'm going to distribute this sign in here. Okay, I'm going to distribute that in. So we're going to have cosine squared of u times sine. Actually, I'm going to write it in a little bit different order. I'm going to write the sine first. Sine of u times the cosine squared of u. And the reason is it just looks exactly like that one. Also, I have two like terms there that I can add together. And if you look up here, that's probably the right thing to do. And then we're going to also multiply the sine of u to the sine squared, which would give us minus sine cubed. And we're one step away here. If you look at that right-hand side, our final answer is going to be combining these two guys together so that we have 3 cosine squared of u times the sine of u. And then we have the minus sine cubed at the end. And we have now verified that identity. A lot of expanding. The math isn't hard. You got to stay organized. You got to make sure you keep parentheses where you need them.